So good morning, everybody. Let's begin our first lecture for today. And it will be, as was announced yesterday, about stochastic variational inference. And one of the state-of-the-art generative models are variational autoencoders. One of the two very popular models together with the generative adversarial networks. We'll discuss GANs as well, but tomorrow and today we'll start with variational autoencoders. So the topic of the lecture is following. First, I will introduce the probabilistic version of a principal component analysis. This is a very known model, and I think that everybody is familiar with it. And we'll see how we can extend it by establishing probabilistic formulation for this model. Then we'll naturally... Меня спрашиваете? I don't know. And then we'll naturally generalize this probabilistic PCA model for nonlinear case and obtain a model known as variational autoencoder. Then we'll have 5 minutes break and continue with discussing how we can propagate gradients through stochastic computational graphs. And we'll consider two methods, reinforce and reparameterization trick. And that will be the end of today's lecture. Okay, so first let's, I think it's too loud. No? Check, check, check. It's okay? Good. So as we remember from yesterday's lecture, we considered latent variable models, and we considered two special cases when latent variables were discrete and when latent variables were continuous. And for the case of continuous latent variables, we discussed that they're very useful for so-called linear representations problem. So that is the case when we deal with high-dimensional complicated data, such as images, graphs, videos, signals, texts, and try to find its inner representations, which are in some sense more informative and more easy for computer to analyze. For example, to define the similarity between different objects. And such models can be written as latent variable models. So we establish a joint distribution over x and z, where x are our observed variables, which are assumed to be high-dimensional data, while z is low-dimensional, they lie in low-dimensional continuous space. And the model can be decomposed as follows, according to the product rule. And we may think of the model as first we generate, for each object, we first generate its latent representation from some prior distribution in low-dimensional space. And then, using this latent representation, we generate the observed variables xi using this likelihood function. So we may think of the general model in such way. And the model is parameterized by parameters theta. So up to now, just like we did yesterday, we assume that we are frequentists and we do not establish any prior distribution over theta. Although, of course, we could do that, but for simplicity, here we decided not to add additional complexity. So theta are just parameters, and we would like to estimate them using maximum likelihood estimation. Since there are latent variables, so the only observable variables are x, so what we would like to do is just to be able to maximize such incomplete likelihood. So this is the likelihood for ith object. If we have a set of objects, we need to take the product of these individual likelihoods and to maximize them as a function of theta. So we can do that it either in direct way or using EM algorithm. And if we use EM algorithm, this is two-stage iterative procedure where on each step we first estimate the distribution over latent representations for each object, and we know that at each step the optimal answer would be the true posterior distribution over the I. And at step we take the expectation with respect to this distribution over latent variables, and we maximize the expected value of log of complete likelihood. Okay, so this is just for short reminding, and now we switch to principal component analysis model. So as we all know, this is a very popular and very simple model which allows to find low-dimensional linear subspaces where the data has as much variance as possible. So we are trying to reduce the dimensionality of the space while keeping the variance. And we know that the answer is given in the closed form. So we simply need to compute the covariance matrix in our high-dimensional space. Then we find the eigenvectors which correspond to the largest eigenvalues, and we project our data to this linear subspace, which is defined by these eigenvectors. So geometrically, it can be shown as follows. So assume that we have two-dimensional space, and we would like to perform dimension reduction in such a way that the most variance is kept, the most variance of the data. So we simply compute covariance matrix, we compute two eigenvectors, we take the eigenvector which corresponds to the largest eigenvalue, and we project our data to this linear subspace. And now let us try to establish probabilistic model which is equivalent to this PCA. So we have a high-dimensional data X, which lives in the space of dimension D large. We also have Latin representations which live in the Euclidean space of dimension D small. We assume that D large is larger than D small, and our joint distribution, our Latin variable model, looks as follows. So again, first we decompose it as a product with respect to each object, because we assume, as almost always, that our data is independent, identically distributed. And then we use product rule. We decompose this joint distribution into the product of likelihood, P of xi given zi theta, times P of zi given theta. And now we need to establish both terms here. So as for prior distribution over the Latin variables, we assume very, very simple distribution. For example, standard Gaussian. And as this likelihood function, we use the following distribution. So this is Gaussian distribution, whose mean is given as a linear function of its Latin representation zi. So we take zi, we apply a linear operator, which converts point from a dimension of D small to the point in the space of dimension D large. We add some mu, and we add some Gaussian noise with the variance sigma squared. So this is the probabilistic formulation of principal component analysis. And what's interesting is that we can easily show, and I leave it as an exercise, that the maximum likelihood solution of this problem, if we observe just x without z, is exactly the answer which we obtain if we use standard PCA. So these models are equivalent, standard PCA model and this probabilistic model. This can be easily shown. What's interesting, instead of just using the straightforward the closed form solution, we can use EM algorithm, because this is a latent variable model. So when we try to estimate parameters, we simply solve this problem. So we simply find the maximum of incomplete likelihood. So the first question to you: how do you think why the closed form solution is available here? Although this is a latent variable model. But instead of using EM algorithm, we may just derive the closed form solution in an analytic form. Yep, exactly. So this is a very simple model, and we can easily see that these two distributions conjugate. This, by the way, was one of the exercises before the summer school, to show that for the mean of Gaussian distribution, the conjugate is a Gaussian distribution. But we can also see it by performing the following considerations. Let's have a closer look to this function. What is this function as a function of z? So this is simply a negative parabola under exponent, right? Because this is Gaussian. Now let's have a closer look to this function. What form has this function as a function of z? Again, since this is a linear function of z, and this is expectation of Gaussian distribution, this function as a function of z is also a negative parabola under exponent. If we multiply the two, it will correspond to the addition of parabolas under exponent, and the sum of parabolas is also parabola. So the result of multiplication will still be a negative parabola under exponent as a function of z. And this means that the two distributions are conjugate. So the result of multiplication will have the same functional form as the prior had. So this means that after applying Bayes equation, if we would like to estimate the true posterior distribution, we'll obtain Gaussian distribution with some parameters, which we need to recompute. So this means that these two distributions do conjugate, and if they conjugate, then we can simply marginalize z in the closed form and obtain the closed form expression for the incomplete likelihood, which we may further maximize. And again, we are likely to have a closed form solution for the theta ML, for maximum likelihood estimate for mesos theta. And this is why PCA works, and this is why in PCA we have a straightforward solution. But instead, we could use EM algorithm. At first glance, it seems idiotic. Why should we use iterative procedure if we have access to the closed-form solution? But interestingly, it appears that in some cases, it can be quite useful. So what are the advantages of using EM algorithm for probabilistic PCA model? First of all is different computational complexities. In the closed-form solution, the computational complexity has this order. So this is O of n times d large squared. Why so? Because we need to compute covariance matrix in the space of X. So we need to sum n objects, and we need to compute d squared coefficients of our covariance matrix. We also need to compute eigenvectors, but this has a cubic complexity. This is d large cube. And since we assume that n is larger than d, this is otherwise the covariance matrix will be degenerate, and the PCA model, well, it's not correct to use PCA in such cases. So since we assume that n is larger than d, then the cubic complexity is dominated by this term. So n d squared, d large squared. This is the computational complexity of a closed-form solution for the PCA model. At the same time, if we start using EM algorithm, each iteration has such complexity. Again, I do not derive it here, but if you wish, you may easily show it as an exercise just by writing down the equations for each step and for m step. So the complexity is less. So this is n times d large times d small. And now assume the following situation. Imagine that our data lives in the space of dimension of 1000, and we would like to perform dimension reduction to the space of, say, dimension 2. So d large equals to 1000, d small equals to 2. And we have, say, 10,000 of objects, so n equals to 10,000. Then each iteration of EM algorithm is approximately 500 times faster than the closed-form solution. And if we assume that EM algorithm takes, say, 100 of iterations to converge, and this is a pessimistic estimate, generally the EM converges much faster, but even if it requires 100 of iterations to converge, we're still 5 times faster than if we use the closed-form solution. So that's a bit unexpected result. So it appears that sometimes in high-dimensional spaces, it's better to use iterative algorithm than using closed-form solution for the PCA. And this is what you should always keep in mind, that sometimes iterative methods work better than just straightforward solutions. What's even more interesting? Okay, that was a quite exotic example. What's more interesting? Now we may process arbitrary subsets of x's and z's as latent variables. Imagine, for example, the following situation. We're given not the x train exactly, but for some objects we have some missing values in the space of x. Imagine more interesting situation. Imagine that for some objects we somehow have access to some values of z. So for example, for some objects we know it's latent representations or at least some coordinates of latent representations. So the question, what should we do? If we use just conventional PCA, it's not extendable. So it's not clear how we can process such situations if we use standard PCA model. But if we formulate it on the probabilistic language, if we formulate it as a latent variable model, we may easily process arbitrary subsets of variables as latents and arbitrary subsets of variables as observed variables. So the ideology remains the same. At each step, we need to estimate the distribution over all latent variables. So if we do not observe some x's, we simply try to estimate the distribution over those x's given the observed data. And since everything is conjugate here, we may easily compute arbitrary conditional distributions. Yep. Please say again in the mic.
So is it always reasonable to assume that the missing random values are always coming from a normal distribution?
Oh, this is our model. This is our PCA model, which states that Z has normal distribution and X given Z has also normal distribution. And the marginal distribution over X is also normal. Sometimes this is a reasonable assumption, sometimes that's not. That's the question of applicability of PCA model. But if we apply PCA model, we assume that everything is Gaussian, actually. Only under this assumption, this method gives us optimal dimension reduction algorithm. So we can process arbitrary subsets of variables as related variables. So this is very nice. So this means that we can correctly, I stress correctly, in an optimal way, process all missing variables and take into account information about the z-values if we have access to some of z-values for some of the objects. And this is again pretty nice. This shows the universal nature of EM algorithm. Everything that is not observable can be treated as a random variable, as related variables, and we simply estimate its distribution over E step, and we take the expectation with respect to this distribution on M step when we maximize the expected value of log of complete likelihood. And the exact division between observed and related variables is not that important. Moreover, there exists Bayesian extension of probabilistic PCA model, which allows also to automatically define the dimensionality of the latent space, to automatically define D. Because in standard PCA model, D small should be set by user. So we have large dimensional data, and we should somehow define to the subspace of what dimension should we project. Sometimes it's obvious, sometimes it's not. There exist the further extensions of the probabilistic PCA model where it's possible to automatically determine the number of hidden dimensions. And if some of you got interested, please refer to Bishop's book where it's described in more details. And one more extension which I would like to describe is the so-called mixture of PCAs. So as we know, PCA is a linear dimension reduction method. So it only allows us to find linear subspace where the related representations live. But in many cases, in many practical applications, there is evidence to assume that data actually lives in a nonlinear low-dimensional manifold, plus some Gaussian noise. So the question is whether we can generalize this PCA model to such nonlinear case. And there are at least two generalizations. One is variational autoencoders, which we'll describe a bit later, and another one is a mixture of PCAs. This is pretty similar to what we discussed yesterday when we talked about a mixture of Gaussians. So let's establish additional set of related variables, this time discrete related variables. So for each object we define a discrete related variable t, which takes values from 1 to k, and we establish the following related variable model, which consists of observed variables x and two types of hidden components of related variables z and t. Z is continuous, t is discrete. And what do we assume? We assume that our data lives in one of several linear subspaces of low dimensional, with low dimensions. And some data comes from one subspace, some data comes from other subspace, some data comes from third subspace. This is well illustrated on this picture. And we have access only to these black points, so no colors are known. And we would like to be able to estimate the parameters of each of those linear subspaces. So what do? First we establish this probabilistic model. So this is prior over t, this is prior over zi. So t is the index of the corresponding subspace from which ith object came, and zi are the coordinates of the ith object in this latent space. So we have two priors, and the likelihood function, which now depends both on ti and zi, is again just a Gaussian distribution, but its parameters are indexed by discrete variable ti. So depending on the index of subspace from which the ith object came in, we have a different linear operator, v of ti, which is applied to the coordinates in this latent subspace, zi, plus some shift, plus Gaussian noise. And all prior distributions for the coordinates in the latent space are standard normal, just like in the probabilistic PCA model, and we also established the discrete prior distribution over the probability of observing each of these subspaces. So the model becomes a bit more complicated, but again, we can use EM algorithm for performing maximum likelihood estimation for the parameters theta. And parameters theta now consist of the set of linear operators, the set of mu's, set of scalars, and probability vector pi. So this is geo distribution. At each step, we try to estimate the posterior distribution over all weighted variables. Since the data is IID, this is simply a product with respect to all objects. And for all objects, we need to estimate the posterior distribution over the i's and ti's, given the observed values, this is xi, and given the current values of the parameters theta. So surprisingly, it appears that we can do it in closed form. Yep, the equation is a bit terrific, but actually there's nothing awful here. This is just a straightforward application of Bayes' theorem. So this is joint distribution over marginal distribution, which we marginalize with respect both to t and with respect to z. So we can compute the true posterior distribution over all weighted variables, and at m step, we simply take the expectation with respect to those weighted variables, and we take the expectation of log of a complete likelihood. So the log of x, z, t, given theta. And we try to maximize it with respect to theta. Again, the solutions, the updates for theta can be obtained in a closed form. So this makes this model mixture of PCAs computationally efficient and practical. And this is an example of weighted variable model where for each object we use both discrete and continuous weighted variables. Okay, now let's switch to a bit more interesting case. So we know that conventional PCA is a linear method, and we also know this is a quite general case when we deal with data which comes from high-dimensional spaces, that in many practical applications, data actually lives in manifolds of small dimension, but the manifolds are highly nonlinear. For example, if we consider the images of 100 to 1000 to 1000 resolution, and each pixel is given by a three-dimensional vector. So this means that each image lives in a 3 million dimensional space. But actually, the realistic images form a manifold of a much smaller dimension than this 3 million space. So in 3 million space, only if we consider complete noise when each pixel is independent on its neighbors, we obtain that such objects live in a 3 million dimensional space. Realistic images live in manifolds of much smaller dimension. The problem is that this manifold is highly nonlinear, and it's not clear how we could restore this nonlinear manifold. But if we have access to the large set of such objects, we could use a flexible nonlinear model with tunable parameters. And probably we all know what is the state-of-the-art model which allows us to restore highly nonlinear dependencies for multidimensional cases when we have access to the large training data sets. That are, of course, deep neural networks. So let us try to build nonlinear generalization of a PCA model. So again, the model is linear variable model, so we need to establish the joint distribution of observed and linear variables, x and y. As before, we'll use IID assumptions, so this is just a product with respect to all objects. We decompose the joint according to the product rule as a likelihood times prior, and prior distribution remains the same. So this is very simple distribution in a small dimensional space. For example, standard Gaussian distribution. Here it is. And we slightly change the likelihood function. In PCA model, we use likelihood function as a Gaussian distribution whose mean was linear function of z, and covariance matrix which was equal to sigma squared times unity matrix. Here we use a bit more complicated model. We substitute as a mu and as our sigma. Well, we use fully factorized Gaussian for simplicity. And as mu and variance, we substitute some nonlinear function of z. And we model those nonlinear functions with the use of a neural network. So mu j and sigma j are the outputs of some neural network, which is parameterized by parameters theta by these parameters. And this neural network takes zi as an input and outputs all mu's and all sigmas in the space of x's as its output. So this is the only modification we did. And this already allows us to construct and to find very nonlinear low-dimensional manifolds for the latent representations of objects. The only question is, OK, so we've defined the probabilistic model. Now the question is whether we'll be able to perform maximum likelihood expectation to find the best values of thetas using just x's. Because we have no access to z. This is a latent variable model. And the problem is, yeah, here we do not have conjugacy anymore. So if we try to marginalize our joint distribution with respect to z, in order to obtain P of x given theta, in order to obtain the objective we should maximize, we immediately will meet the problem of non-conjugacy. So this integral is not tractable. The reason is trivial. The reason is because those functions are no more linear functions of z. If they were linear, there'll be full conjugacy. But since these are non-linear functions, which are modeled by a neural network, there's no more conjugacy. So this means that we can't directly optimize incomplete likelihood. Just the thing we could do in standard PCA model, where we could compute P of x given theta in a closed form, and we could optimize it directly and obtain a closed form solution. Here, this is not possible anymore. OK, so now what about EM algorithm? Well, in the EM algorithm, at each step, we need to estimate the distribution over the latent variables. Again, since the data is IID, will be given by the product of distributions of latent variables for each object. And the optimal answer is the true posterior distribution, P of zi given xi theta. But again, due to the absence of conjugacy property, the expression for this optimal for the true posterior distribution is intractable. So we can't compute this true posterior distribution. But what we can do? Actually, we know that this answer, that Q of zi should be equal to the true posterior distribution, is derived from the derivation of the EM algorithm, where we had to minimize KL divergence between our Q distribution and the true posterior. And if we have access to the true posterior, we simply say that our Q distribution equals true posterior. But if we can't compute the true posterior, we can still use variational Bayes. We can still perform variational inference and approximate the true posterior with some tractable approximation, with some tractable Q distribution, by minimizing KL divergence between Q and between the true posterior. OK, let's try to do that. And unlike yesterday's lecture, where we used the factorization assumption, here we'll limit our variational family, our variational distributions by some parametric family. And in particular, we'll try to approximate each posterior distribution for each object with the following parametric approximation. So this is Q of zi, which takes xi as an input, and which is parameterized by 5 parameters. And the distribution itself has the following form. So this is fully factorized Gaussian distribution in the low-dimensional space, in the space of D small. And for each coordinate, each mu and sigma squared are given as some nonlinear function, which depends on xi, and which is parameterized by parameters phi. And again, since we have some parameterizable nonlinear function, it's very reasonable to use deep neural networks to model this nonlinear function. So this means that we'll model this Q distribution by another neural network, which is parameterized by parameters phi. And this is exactly variational auto-encoder model. So we have 2 neural networks, encoder and decoder. Encoder is parameterized by phi. It takes x as an input. So the input is in the space of dimension d large. And it outputs the parameters of a Q distribution, d small mu's and d small sigmas. So these are the parameters of fully factorized Gaussian distribution in the space of Z, so in the space of latent variables. And the second network is decoder or generator, which takes Z as an input. So the input has dimension d small, and outputs the vector of parameters for the distribution for our algorithm, for the distribution of x given Z And the output is, has dimension 2 times d large. So d large values for the mu's and d large values for the sigmas. So these two networks together form the model variational autoencoder. And now let us think how we can train this model. So how we can tune the parameters theta and the parameters phi. Remember that our goal is to maximize incomplete likelihood. Incomplete likelihood, so that is P of X train, the probability of observing what we observe in our training sample, given theta. So for, as we know, if we perform variational inference at each step, we have to minimize KL divergence between our variational approximation Q and the true posterior distribution P of Z given X theta. And as we know from yesterday's lecture, such minimization problem is equivalent to the maximization of variational lower bound. So here we write down the variational lower bound. It should be already familiar to you. So this is the expectation with respect to our variational approximation Q of log of density ratio, joint distribution over X and Z, which are here decomposed as a product of likelihood times prior, over Q. If we optimize this variational lower bound with respect to phi, we'll obtain exactly this problem. So we'll try to get better and better approximation for our true posterior distribution. And if we optimize this variational lower bound with respect to theta, we'll obtain M step in M algorithm. So here we have variational lower bound, which depends on two groups of parameters, phi and theta. Phi defines our variational approximation, theta defines our probabilistic model. And just like in EM algorithm, where at each step we optimize with respect to our variational approximation, and we try to update Q distribution to be as close as possible to the true posterior, and at M step we optimize the parameters of model itself, the parameters theta. Here we have the same situation. The only difference is that we limited our Q distribution to belong to some parametric family, and the parameters are given by phi. So then instead of function optimization here, we obtain the parametric optimization with respect to parameters phi. So we need to optimize this variational lower bound both with respect to phi and with respect to theta. Of course, we could do the block coordinate optimization just like we did in EM algorithm. So we can fix theta, we can optimize with respect to phi, then we can fix phi and optimize with respect to theta, and so on until convergence. This is correct procedure, it will work, but it will take years to converge. Because at each iteration, we'll have to numerically solve optimization problems. Because there are no more closed form solutions for the optimization with respect to phi, given theta fixed, and to the result of optimization with respect to theta, given phi fixed. No more closed equation. And then the idea is pretty simple. If there are no closed form expressions for block coordinate optimization, then let us optimize jointly and simultaneously with respect to phi and theta. And let us simply make gradient steps in the space of theta and phi at the same time. Okay, this sounds reasonable, but still I have two problems. So one problem is that when we talk about deep neural networks, we usually assume that our training data is large, because only in these settings deep neural networks really show state-of-the-art behavior. If our data is very limited, then it's better to use linear models such as PCA. So we, yep.
So is the problem here that if phi is fixed, then it's okay to compute the expectation, because then you can sample from Q and then plug it into those and get an insane estimate of the but if phi is fixed, then it's very problematic. Is that the problem?
No, you said two things.
So basically, you said that it was a problematic
Yep.
optimization.
Yep.
So there are two things which are changing, phi and theta. So if we keep the phi fixed, then we have the Q distribution, which is
So phi is fixed.
yeah.
Okay.
So then we can sample from the Q distribution because X and phi are known.
We can sample from Q distribution. Yep.
And then compute that log ratio.
But only very approximately.
Yeah. So it might. Okay.
So we can compute it, but this will be just Monte Carlo approximation. So we will not be able to obtain closed form solution for argmax of this guy with respect to theta, even if phi is fixed. And the similar considerations apply to the optimization with respect to phi if theta is fixed. So, and then there's no reason why we should perform the block coordinate updates. We can optimize this variational bound simultaneously with respect to phi and theta by making gradient steps. But still, there are some problems. So as I thought, we assume that the training data is large. And when it's large, then the computational complexity of computing exact gradients will be quite expensive, because we'll need to sum over with respect to all objects in our training data set. But the second problem is even worse. So we know how to overcome the first problem. We simply will use mini batches of data, and we'll switch to stochastic gradients. But the second problem is a bit more complicated, and it's related to the fact that this integral is intractable. And this is really so. Although this is Gaussian distribution, although these are Gaussian distributions, but due to the nonlinear dependencies between z and x, here and here, the integral becomes intractable. And we have to optimize this integral, although it's intractable. And the solution is a so-called doubly stochastic variational inference procedure. Okay, now let us see how we can compute gradients, stochastic gradients with respect to theta and stochastic gradients with respect to phi. Let's start with the theta as a more simple case. So this is our objective, and we perform to get stochastic gradients, first we perform mini batching. So the gradient of our variational bound is given by this equation. So again, this multidimensional integral can be split into the sum of integrals with respect to each zi, due to the fact that the objects are IID. And the nice thing is that here the joint distribution is under logarithm. So the joint distribution is just a product. And since it's under logarithm, it becomes sum of logs. And due to this, we may significantly reduce the dimension of the space where we take the integral. So instead of integrating with respect to all z large, we have the sum of integrals, and each integral is in the space of zi. Okay, this is nice, but the integral is still intractable. Okay, now what do? We put the differentiation inside of expectation. Here we split the log into two parts. We notice that these guys do not depend on theta, so only this term depends on theta. And our gradient converts to this form. And now we perform mini batching. Instead of performing all summation with respect to all objects in our training data set, we take just one by random, or several if we want. Here for simplicity I took just one. So I sample from uniform discrete distribution from 1 to n. I take ith object, and I compute gradient only for the ith object. And of course, I should multiply the gradient by n in order to get unbiased estimate. So this is approximation, but what is good is that this value is unbiased estimate to the true gradient with respect to theta. Okay, good, but the integral is still intractable. So what will I do next? How to get rid of this intractable integral and to keep the unbiasedness? Yeah, sure. Now we can remove this integral, which is intractable, with its Monte Carlo estimate. So all I should do, I simply sample from this distribution. I sample the I star, and I substitute it into sub-integral expression. And then I may say that this expression, n times gradient with respect to theta of log of p of xi given the I star theta. If I differentiate it with respect to theta and multiply by n, I will obtain unbiased estimate to the true gradient of our variational bound with respect to theta. And this procedure is known as a doubly stochastic procedure, doubly stochastic variational inference. Why doubly stochastic? Because we use stochasticity twice. First, we use it when we switch to mini batch of data. And secondly, when we remove this integral with its unbiased estimate obtained by Monte Carlo estimation. So this is pretty nice. Since we already have stochastic gradient, there's no harm to use another stochasticity, because we already have a stochastic gradient rather than full gradient. So this is the procedure how we can compute stochastic gradients with respect to theta. And now let us have a 5-minute break, and then we'll continue computing stochastic gradients with respect to phi, which will be a bit more complicated. So, and while we're waiting for the others, the question to you guys, why can't we use the same trick for computing the stochastic gradient with respect to phi? So this was our equation for stochastic gradient with respect to theta of variational bound. But it is not the case for the gradient, for stochastic gradient with respect to phi. Okay, the last line, right. So what is the problem with the stochastic gradients with respect to phi? Here we have expectation of log of density ratio, right? But the distribution with respect to which we compute expectation itself depends on phi. So we can't move the differentiation inside of expectation. We can move it inside of integral, but not inside of expectation. And this is pretty bad. So this is what is illustrated by this line. So assume that we have a expectation of function h over x, y, and we take expectation with respect to y, but the distribution over y depends on x, is conditioned by x. And we would like to compute gradient or stochastic gradient with respect to x. So we can't move this differentiation inside of expectation. So we can't move it right here. Okay, but what we can always do is to move a differentiation inside of integral. So what's the problem then? So we can always do the following derivation. So we move differentiation inside of integral, and now we can use the product rule for computing derivatives, right? Okay, let's try to do that. So this is again our example. The expectation of function h, which depends on x and y, and the expectation is taken with respect to distribution p of y given x. So we compute the expectation with respect to y, and we try to differentiate the resulting expectation with respect to x. If everything is continuous and differentiable inside the integral, then we can move the differentiation into the integral. So we have derivative of the product. We use the standard product rule for computing derivatives. And we end up with these two integrals. What's the problem with them? Of course, we assume that the integral is intractable. Otherwise, it's not interesting, and we can differentiate it straightforwardly. But if the integral is intractable, what we would like to do is to move the integral with its unbiased Monte Carlo estimate, right? What's the problem with these two terms? Yep. So the first term is OK. So this is still an expectation with respect to some distribution of some function. And we may simply remove it with the Monte Carlo estimate by generating y hat from this distribution and substituting y hat here. And then we get rid of the integral. Of course, we obtain stochastic estimate. It has some variance, but at least it's unbiased. So we keep all theoretical guarantees of the corresponding optimization procedure. But here, this integral is not an expectation. So it's not clear how to remove it with its unbiased estimate. And the standard way to proceed is to use so-called log derivative trick. I guess many of you are familiar with it. So to make use of the following identity. The derivative of p with respect to x equals to the p times the derivative of log p with respect to x. So this is standard trick known as log derivative trick, and well, it's quite obvious. If we differentiate the log, we'll obtain 1 over p. It will vanish with this p, and we will obtain just the derivative of p. So if we will use it, the second term becomes an expectation. So this is an expectation with respect to p of y given x. The expectation of what? H function times the derivative of log of p. Now both terms are expectations, and we can remove them with the unbiased Monte Carlo estimates. Yeah, so this is it. Now let's return to our variational bound. So this is how we obtain unbiased estimate for this stochastic gradient for this case. So we simply sample from p of y given x, y0, and we substitute it into here and into here. And the sum of these two terms gives us unbiased stochastic estimate to the true gradient of the left-hand part expression. So now let us return to our ELBO function. So this is it. This is expectation with respect to Q, the expectation of log density ratio, P of x given z times P of z over Q of z. And we also know that P of z is Gaussian distribution. Q of z is also Gaussian distribution. So this was our prior, this is standard Gaussian, and this is our variational approximation that is by assumption is also fully factorized Gaussian distribution. So we may split this log into two parts. And the second part will be KL divergence between our variational approximation and the prior distribution, just like we did yesterday. And the nice thing is that this KL divergence can be computed in a closed form, because this is KL divergence between two normal distributions. So it's known how to compute it. There are closed form equations. So we can compute it analytically and then differentiate the result with respect to phi. So everything is fine here. And the only intractable part is here. So this is the expectation with respect to Q of log likelihood of our training data. And we need to differentiate it with respect to phi. And again, we can use the result from a previous slide and perform a log derivative trick. And at the same time, we perform a mini batching. So we take just one object from our training data set by random, ith object. And then we use log derivative trick and sample zi star from this Q distribution and obtain the following expression. So this is log likelihood of ith object at the condition that at the point zi star, which is a sample from our Q distribution, times the derivative of log of Q with respect to phi. And we have to multiply it by n. So this is the unbiased estimate for stochastic gradient of our variational bound with respect to phi. So far, so good. But there's something bad with this procedure. And now let's understand why almost nobody uses these log derivative tricks in practice. And to do that, let us first examine what is the derivative of log of Q with respect to phi. In probability theory, this function is known as score function, and it has a quite nice property. So this is function, if zi is random variable, this is random function, and it has a nice property that its expectation equals to exactly 0. So this is the derivation. It's really quite trivial. So let us consider this log derivative and compute expectation with respect to Q distribution. So we use log derivative trick. We obtain Q over 1, Q times 1 over Q. They vanish. And this is just the derivative of Q. We can move the derivative outside the integral. Then there'll be integral of probability density function, which equals to 1. And the derivative of 1 is identical 0. So this means that this function has expectation 0. Or in other words, if we return to the stochastic gradient, so here we use random samples, zi star, samples from Q distribution. So this is a random variable, and it oscillates around 0. Sometimes it's a bit higher, sometimes it's a bit less, but in expectation it has 0. And this oscillating function we multiply by what? By log likelihood of ith object times n. And then if we have a huge data set, say consisting of tens of thousands of objects, then it appears that we multiply some oscillating function, some function which oscillates around 0, by huge value. So the log likelihood of each object is usually is already pretty high, at least at the early stages of training. But we also multiply it by n, which is huge. And this leads to the fact that this value, so this is stochastic gradients, and it has extremely high variance because of this multiplier. So for example, the expectation of this stochastic gradient can be, say, 1.5, and the individual samples with individual zi's can be of orders of millions. So this is completely impractical procedure. Formally, this is correct procedure, formally. So it gives us unbiased estimate to the true gradient of variational bound with respect to phi. But since it has huge variance, it's completely useless. Because we know from stochastic optimization theory that the larger is variance of our stochastic gradients, the less is the conversion speed. So if our stochastic gradient has extremely high variance, then the convergence will be extremely slow. So it will take not even years, ages to converge. And this is why this procedure, known as, by the way, reinforced algorithm, is almost never used. The partial solution of this problem could be the use of so-called baselines, and there will be next lecture where Artem Sobolev will give a talk and will review several cases when it becomes possible to reduce the variance of this stochastic gradient. Roughly speaking, the idea is pretty simple. We need to add some random variable here which has zero mean and which somehow vanishes the large portion of the variance of this unbiased estimate. Sometimes this is possible. For example, some random variable which is negatively correlated with this expression and which has zero mean. So if we add it, the mean will be the same. So it will still be the unbiased estimate to the true gradient. But if it's negatively correlated with this guy, they will compensate the variances of each other up to some limit. So, and more details will be in upcoming lectures. So I will not give them now. So to summarize, this table shows how we can compute stochastic gradients for different objective functions. And you should realize that the stochastic gradient is the key ingredient to scalable versions of traditional machine learning algorithms. So anytime when you want to scale your model, to scale your machine learning model to large data or to large dimensions, you should ask yourself whether it's possible to switch to stochastic gradients. Because only the transition to stochastic gradients allows us to build computationally efficient procedures for the case of large data sets. So imagine that our objective function is simply sum of large number of items fi of x. And we would like to obtain gradient or stochastic gradient for f of x. So of course the solution is trivial. So we simply take one item by random. So we sample I from uniform distribution from 1 to n. We take fi, we compute its gradient, and we multiply it by n. And we obtain unbiased estimate to the true gradient of function f. Now the function f is just expectation of function h, which depends on x and y, and we take expectation with respect to y. And we would like, so this is the function of x, and we would like to get stochastic gradient with respect to x. So again, the solution is pretty trivial. We simply substitute Monte Carlo estimate instead of this integral. So we sample y0 from P of y, we substitute y0 here, and we differentiate this subintegral function with respect to x. The third line is simply the combination of the first two. And finally, the last line. So it looks pretty similar to the second line. The only difference is that the expectation now itself is dependent on x. And then if we'd like to get unbiased stochastic estimate for the true gradient of this function as a function of x, we need to use this reinforced algorithm, and the stochastic gradient will consist of two parts. The first part is the same as in the second line, but there's also some addition. And this addition is caused due to log derivative trick. So we sample y0 from our distribution, from P of y given x. We substitute it into h function and differentiate it with respect to x. But we also have to take h function at the point x, y0 and multiply it by log derivative of P of y0 conditioned on x, derivative with respect to x. So this is exactly what we have derived a few slides above. And the problem is that the last expression generally has a very large variance, and we need to use some kind of variance reduction techniques that we'll study in the next lecture. Okay, yep.
So why do you only sample a single point when you calculate the stochastic gradient?
The answer is just for simplicity. Of course, we can use several objects here, several items here, and we can use several samples here. If we use several samples, we'll reduce the variance. This is right. The problem is that we can reduce the variance in several times. And here, we have to reduce the variance in several orders of magnitude. So it's too high, and sampling several times doesn't help here. We can sample several times here, right? But when we sample several times, the computational complexity of making one iteration of stochastic gradient increases. So there's always a compromise. But here, for simplicity, I assume that we take just one item from this summation, and we take just one sample from this distribution. But of course, we may take several. Okay, and the problem of large variance of reinforced algorithm was so severe, and there was so much need to come up with some efficient procedure that allows to differentiate variation over bounds with respect to variation of parameters phi, that the way out was invented independently by 3 groups in 2014. And this is what is known as reparameterization trick. So the idea is pretty elegant and pretty simple. So again, consider that we would like to differentiate such expectation where the density function itself depends on the parameters x with respect to which we would like to compute gradient. What can we do? We can try to express the y variable as some deterministic function g, which depends on the condition, on x, and depends on a random variable epsilon, which comes from unconditional distribution, which is some parameter-free distribution. If we manage to do that, then we can perform change of variables equation and convert this integral into this one. So imagine that we somehow manage to express y as a function of g, of x, and epsilon. Then instead of taking expectation with respect to this conditional distribution P of y given x, we can equivalently compute the expectation with respect to some parameter-free distribution r of epsilon. And the subintegral function will be h of x, comma, g of epsilon x. And this is, in some cases, this is possible, and probably the classical example is arbitrary Gaussian distribution. We all know that we can express arbitrary Gaussian via standard Gaussian distribution, right? We take sample from standard Gaussian distribution, we multiply it by standard deviation, by sigma, and we add mu. And we obtain sample from the arbitrary Gaussian distribution with a mean mu and with a variance sigma squared. Yep. Okay, I got the question.
Where did R come from?
Well, that depends on a particular form of this distribution. For example, let us assume that this distribution is one-dimensional Gaussian distribution with the parameters mu and sigma. And the mu and sigma play the role of this x. So this distribution is conditioned on the mu and sigma. We can always say that then y can be expressed as follows: epsilon times sigma plus mu, where epsilon comes from standard normal distribution with zero mean and unit variance. And then, and this is our epsilon, some standard distribution which we can use for expressing our conditional distribution over y. This is not always possible, but sometimes it is. And I will show in the next slide. Oh, actually, I can show it already now. So if we have one-dimensional Gaussian distribution, as our epsilon, we can use just standard Gaussian distribution. And the g function looks as follows. And as a y, we have mu and sigma here. The same consideration applied to gamma distribution just for the second argument. If the first argument is fixed and is known, then the reparameterization looks like this. For the exponential distribution, we can express it from as a function of uniform distribution from 0 to 1, and a multidimensional Gaussian distribution, which again can be expressed as some function of a standard multidimensional Gaussian distribution. There are some more examples, but this is always ad hoc procedure. So not all distributions are reparameterizable. But if we are lucky enough, and if our distribution P of y given x is reparameterizable, then we can use this g function. We can convert this integral to this integral, where the expectation is taken with respect to a random variable that doesn't depend on any parameters. And then we can move the differentiation inside of expectation. So we do that, and then we simply sample from our epsilon hat. We substitute it here, and now we have to compute the derivative with respect to x of h of x, comma, g x epsilon hat. And again, pay attention that now we'll have to differentiate twice, first with respect to the first argument, and then we need to differentiate h with respect to the second argument, and differentiate the second argument with respect to x. But this is, well, standard rules for computing full derivative, which we know from calculus courses. And surprisingly, it appears that such method, so it also provides us with an unbiased stochastic estimate for the true gradient. But this stochastic gradient has much less variance, orders of magnitude less variance. This is why it was really a breakthrough. It happened 5 years ago. This is why it was invented independently in 3 groups at the same time, because all of those 3 groups worked with deep Bayesian models, and they crucially needed to have some procedure which allows to get low variance stochastic gradients for variational or bounds. So, and this is what you should always do if your random variable is reparameterizable. Yep.
So you mentioned on the previous slide that some discrete distributions cannot be reparameterized. Sorry.
Actually, this is the next slide.
I think there are some relaxations from the categorical distribution.
Yep.
Actually.
Yep. I will mention it a bit later. Okay. Yep. So just as was told. Well, first, not all continuous distributions are reparameterizable. So you should always monitor whether you can do reparameterization or not. But in practice, almost everybody uses just multidimensional normal distributions, and they're known to be reparameterizable. What is worse is that discrete distributions can be reparameterized. Well, actually speaking, they can. We can reparameterize discrete distributions, and we can express them as a sum function g of some random variable epsilon, but the problem is that since those distributions are discrete, function g will be non-differentiable. Right. So this means that we can't compute this derivative. And this is why a reparameterization trick is not straightforwardly applicable to discrete random variables. And again, this causes serious problems because many research groups do like to work with latent variable models with discrete latent variables, and they also needed some way of computing stochastic gradients. And again, as happened with reparameterization trick, the solution, known as Gumbel softmax trick, was independent by 2 groups simultaneously, and they were presented at the same NIPS conference in 2017, if I'm not mistaken. So these were the groups from DeepMind and from Google Brain. I wonder whether they communicated to each other at the stage of developing. Maybe, maybe not. But they really presented 2 papers which suggested the same way out of how we can relax this assumption, of how we can generalize reparameterization trick for the discrete variables. And in the next lecture, you will be given this Gumbel softmax trick as well. Okay, so now let us return to our variational bound. It has this form. We would like to get derivative, or at least unbiased estimate for the derivative with respect to phi. So, and using reparameterization. So first we use mini batching as before. So instead of differentiating the sum with respect to all objects, we take just one object by random. So we did that. And then we perform a reparameterization trick. So we express our zi variable as a sum function g, which depends on epsilon, on xi, and on phi, where epsilon is just some standard distribution. And in our case, since Q distribution is a fully factorized normal distribution, so for epsilon, we use just standard normal distribution. So then we convert this expectation into the expectation with respect to standard normal distribution. And now we may move differentiation inside of expectation, sample epsilon hat from our standard distribution, and obtain this expression for the stochastic gradient. So this is how it works, and now we're able to write down the final algorithm of how we can train variational autoencoder, how we can tune the weights of encoder and decoder networks. So as an input, we take the training data. This is only x. We do not observe z's. And the dimension of a latent space, d small. And at each iteration, we simply take one or maybe several objects as our mini-batch and compute stochastic gradients of our variational bound with respect to theta and with respect to phi, according to the equations we have just derived. And we continue our optimization process until convergence. And since both stochastic gradients are unbiased, so we compute unbiased estimate for the true gradient of our variational bound we are guaranteed to converge according to the properties of stochastic gradient methods. And of course, you may use your favorite stochastic optimization tools, for example, SAG, ADAM, or whatever. So what is good in variational autoencoders? We have the same objective, variational over bound, which we maximize with respect to both groups of parameters, phi and theta. And this ensures, this gives us guarantees that this optimization procedure is very robust, it's very stable, and it's always converges. If we compare it with a concurrent model, concurrent popular model, known as generative adversarial networks, I think you're all familiar with it as well. In GANs, we have generator, we have discriminator, and we have different objective functions for discriminator and for generator. All objective functions depend on both groups of parameters, on both the parameters of generator and discriminator, but we optimize one objective function for discriminator, another objective function for generator. And these functions are often in conflict with each other. And this leads to very unstable oscillating behavior, which has been reported many times for generative adversarial networks. So unlike GANs, in the variational autoencoder, everything is very robust, because with both groups of parameters, we optimize the same objective function. And we maximize it both with respect to theta and both with respect to phi. So this is a much more stable procedure. So what are other pros and cons in comparison of variational autoencoders versus generative adversarial networks? Of course, we all know that, well, here I'm afraid it's not seen clearly. I wonder why. But we all know that generative adversarial networks tend to produce more realistically looking objects. This is especially true when we discuss the generative models for images. So we know that images produced by GANs look more nicely than images produced by variational autoencoders, where they tend to be always smooth. But the price to pay is that generative adversarial networks suffer from so-called mode collapsing. So they're able to generate very nicely looking images, but they cover only a tiny subset of our training data. So they're not able to generate all objects from our training data, or objects that look pretty much the same like arbitrary object from training data. And this property is known as mode collapse. So they cover only some small subset of the distribution from which our objects came. To the contrary, variational autoencoder covers the whole training data set. So it's able to generate any object from our training data set. And the problem is that sometimes it also generates some objects which are out of domain. And just like what we see here, when the objects are over-smoothed and they're not realistically looking. So both generative models have its own advantages and bottlenecks. This is why we can't say that one model is definitely better than another. And for some applications, it's better to use GANs. For some applications, it's better to use variational autoencoders. For example, if we consider, say, the problem of synthesis of new molecules, of new organic molecules. This is one of the projects on which one of my PhD students is working over now. Then it appears that GANs are completely useless for these purposes because of mode collapse, because they even can't synthesize the molecules from training data, not saying about synthesizing unseen molecules. While variational autoencoder is ideal for such case because it's able to synthesize everything it saw in the training set, and it may generalize and it may synthesize some new unseen structures. If we speak about synthesizing realistically looking images, then probably it's better to use generative adversarial networks, but again, it depends on the application. And of course, one of the holy grails of a modern machine learning community is to build some kind of unifying model, such model for which the variational autoencoders and the generative adversarial networks could be just some particular cases. This is very promising trend, and there are several works already which try to bridge the gap between VAE and GAN. I will just mention just a few of them. Is that adversarial autoencoders, adversarial variational Bayes, implicit variational autoencoders, and there are some other attempts. There's not clear success yet, but I believe that in the next years, we'll see that someone will invent the unifying model, which takes the best of the two worlds, of the world of variational autoencoders and of the world of GANs. Okay. So I'm afraid I have too little time, so probably I will skip the last part about the differentiation of stochastic computational graphs, but the presentation is online, so if you got interested, you may visit it. It's not difficult at all, although there are quite a lot of slides remained. So here I will finish. This is yeah. So this is the conclusion. Today we got familiar with the variational autoencoder, which is one of the state-of-the-art generative models. It's Bayesian. It's natural generalization of a probabilistic PCA model for the nonlinear cases, and it really allows us to build low-dimensional, highly nonlinear manifolds for our high-dimensional data. We also got familiar with the tools how to compute stochastic gradients for variational or bounds, and this is our main objective when we are speaking about deep Bayesian models. So we got familiar with the reparameterization trick as some specific tool for computing low variance stochastic gradients, and we also got familiar with the reinforced algorithm that is a general tool, which is always applicable, but the problem is that it has much larger variance, but sometimes this variance can be reduced, and this will be the topic of next lecture, as well as the Gumbel softmax relaxation. So up to now, there's an open problem how to deal with the discrete latent variables, but fortunately, before afternoon, you'll get familiar with this technique as well. So that's all. Now I'm open for the questions, if any.
Is there an intuition behind why VEs don't suffer from mode collapse? And if you remember from yesterday, the posterior distribution approximation does something like
I got the question. There are some theoretical results that justify that this mode collapsing is inevitable if we are operating with non-optimal discriminators. This is always the case. So if the discriminator is ideal, there'll be no mode collapse. But if discriminator is not ideal, and we always operate with a non-optimal discriminator, then the problem of mode collapse is inevitable when we perform adversarial training. There are some theoretical results. But unfortunately, I do not have intuition why it happens.
Thank you.
Do we understand right that the reason that wires generate smooth pictures is due to the fact that likelihood is factorized on per pixel Gaussian distribution, and GANs don't, and this is not the case for GANs because they do not take this assumption?
There are several reasons why variational encoders produce over-smooth images. One of them is the one you mentioned. Another of them is that we use too simple likelihood function that is a Gaussian distribution in the space of pixels, and it also tends to over-smoothing. So there are at least two reasons. Yeah.
Can you please explain once more why reinforce has large variance?
Yep, sure.
Thanks.
So in the reinforced algorithm, this is the expression for stochastic gradient. So there is some multiplier which has a huge absolute value. Huge absolute value because we multiply it by n, and n is large. N is the size of our training data. Times some random function which has zero mean. So it oscillates around zero. And if you now imagine some oscillating function around zero which is also multiplied by, say, 1 million, you'll get something with a very huge variance. And what is even worse is that not only the variance is huge, but this quantity can be either positive or negative. So we can't even define the true direction of gradient. So we may go to the opposite direction because of these oscillations of score function. Yep.
Hi. So I had a question related to the decoding network that you have, because you mentioned that you calculate the parameters as a mean and a standard deviation for the decoding part. But usually they make a choice where they choose a constant standard deviation. Like, what would be the implications if you don't choose it as fixed? And why do we do it?
Well, in practice, in most of cases, you're right, and the people usually model the variance for the distribution just a single parameter, so they don't model it for different components individually. So this is also possible. This model is a bit more rich, and this was how it was originally formulated. So this model allows us to get a better description of our training data, because we have more flexible probabilistic model. But of course, it involves much larger number of parameters, because here we have the output of dimension of 2D large. So in practice, if D large is sufficiently large, and this is almost always the case, the people use just one variance for all the components.
Okay. So it's like for efficiency related things. Okay, thank you.
Okay, if there are no questions, let us now have a 30 minutes break. And thanks very much for your attention. This was my last lecture, so all other lectures will be given either by my PhD students or by invited speakers. Thanks.